Fireproofing is rendering something proof against fire, or incombustible, or material for use in making anything fireproof. It is a passive fire protection measure. Fireproof, or fireproofing can be used as a noun, verb or adjective. It may be hyphenated. Applying a certification-listed fireproofing system to certain structures allows them to have a fire resistance rating. The term fireproofing may be used in conjunction with standards, as reflected in common North American construction specifications. An item classed as fireproof is resistant in specified circumstances, and may burn or be rendered inoperable by fire exceeding the intensity or duration that it is designed to withstand. Markets: commercial construction, residential construction, industrial construction, marine, offshore construction, aerodynamics, tunnel concrete walls and ceilings or linings, under and above ground mining operations. Patrick Kabikungan. Applications: structural steel to keep below critical temperature circa 540 degrees Celsius, electrical circuits to keep critical electrical circuits below 140 degrees Celsius so they stay operational, liquefied petroleum gas containers to prevent a BLEVE, vessel skirts and pipe bridges in an oil refinery or chemical plant to keep the structural steel below critical temperature circa 540 degree, concrete linings of traffic tunnels. History: asbestos was one material historically used for fireproofing either on its own, or together with binders such as cement either in sprayed form or in pressed sheets, or as additives to a variety of materials and products, including fabrics for protective clothing and building materials. Because the material was later proven to cause cancer in the long run, a large removal and replacement industry has been established. Endothermic materials have also been used to a large extent and are still in use today, such as gypsum, concrete and other cementitious products. More highly evolved versions of these are used in aerodynamics, intercontinental ballistic missiles and re-entry vehicles, such as the space shuttles. The use of these older materials has been standardized in old systems, such as those listed in BS 476, DIN 4102 and the National Building Code of Canada. Alternative fireproofing methods. Among the conventional materials, purpose-designed spray fireproofing plasters have become abundantly available the world over. The inorganic methods include gypsum plasters, cementitious plasters, fibrous plasters. The industry considers gypsum-based plasters to be cementitious, even though these contain no Portland or calcium aluminate cements. Cementitious plasters that contain Portland cement have been traditionally lightened by the use of inorganic lightweight aggregates, such as vermiculite and perlite. Gypsum plasters have been lightened by using chemical additives to create bubbles that display solids, thus reducing the bulk density. Also, lightweight polystyrene beads have been mixed in their plasters at the factory in an effort to reduce the density, which generally results in a more effective insulation at a lower cost. The resulting plaster has qualified to the A2 combustibility rating as per DIN 4102. Fibrous plasters, containing either mineral wool or ceramic fibers, tend to simply entrain more air, thus displacing the heavy fibers. On-site cost reduction efforts, at times purposely contravening the requirements of the certification listing, can further enhance such displacement of solids. This has resulted in architects specifying the use of on-site testing of proper densities to ensure the products installed meet the certification listings employed for each installed configuration, because excessively light inorganic fireproofing does not provide adequate protection and are thus in violation of the listings. Proprietary boards and sheets, made of gypsum, calcium silicate, vermiculite, perlite, mechanically bonded composite boards made of punched sheet metal and cellulose-reinforced concrete have all been used to clad items for increased fire resistance. An alternative method to keep building steel below its softening temperature is to use liquid convection cooling in hollow structural members. This method was patented in the 19th century, although the first prominent example was 89 years later. Substandard fireproofing. Money can be saved fraudulently by using apparently suitable fireproofing that is not built to the required standard. Such fraud can be prevented when documentation is required and checked to ensure that all installed configurations meet the certification standards. Possible cases include, entraining too much air in inorganic systems, thus reducing densities below fire-tested, saving on materials and labor. Spraying inorganic fireproofing materials over through penetrations and building joints that should be fire-stopped, not fireproofed. This practice negates fire separation integrity. Fire stops must precede spray fireproofing. Substitution of incandescent and/or endothermic fireproofing coatings by less expensive paints of similar appearance, sometimes in the packaging of the correct materials. The American and Canadian nuclear industries have, historically, not insisted on listing and approval use and compliance, on the basis of the use of accredited certification laboratories. This has allowed the use of Thermolag 330-1, for which the basis of testing has been proven to be faulty, requiring millions of dollars of remedial work. The Thermolag scandal came to light as a result of disclosures by American whistleblower Gerald W. Brown, who reported the deficiencies in fire testing to the Nuclear Regulatory Commission. As of 2014, certification of fireproofing and fire-stopping remained optional for systems installed in nuclear power plants in Canada and the United States. Reuse of older materials from demolished buildings, in newer buildings. Work staging, spray fireproofing products have not been qualified to the thousands of fire-stop configurations, so they cannot be installed in conformance of a certification listing. Therefore, fire-stopping must precede fireproofing. Both need one another. If the structural steel is left without fireproofing, it can damage fire barriers and a building can collapse. If the barriers are not fire-stopped properly, fire and smoke can spread from one compartment to another. Traffic tunnel fireproofing. Traffic tunnels may be traversed by vehicles carrying flammable goods, such as petrol, liquefied petroleum gas and other hydrocarbons, which are known to cause a very rapid temperature rise and high ultimate temperatures in case of a fire. Where hydrocarbon transports are permitted in tunnel construction and operations, accidental fires may occur, resulting in the need for fireproofing of traffic tunnels with concrete linings. Traffic tunnels are not ordinarily equipped with fire suppression means, such as fire sprinkler systems. It is very difficult to control hydrocarbon fires by active fire protection means, and it is expensive to equip an entire tunnel along its whole length for the eventuality of a hydrocarbon fire or a BLEVE. Concrete exposed to hydrocarbon fires equals, concrete cannot by itself withstand severe hydrocarbon fires. In the Channel Tunnel that connects the United Kingdom and France, an intense fire broke out and reduced the concrete lining in the undersea tunnel down to about 50 mm. In ordinary building fires, concrete typically achieves excellent fire resistance ratings, unless it is too wet, which can cause it to crack and explode. For unprotected concrete, the sudden endothermic reaction of the hydrates and unbound humidity inside the concrete generates pressure high enough to spool off the concrete, which falls in small pieces on the floor of the tunnel. Humidity probes are inserted into all concrete slabs that undergo fire testing to test for this, even for the less severe building elements curve. The need for fireproofing was demonstrated, among other fire protection measures, in the European Eureka Fire Tunnel Research Project, which gave rise to in-building codes for the trade to avoid the effects of such fires upon traffic tunnels. Cementitious spray fireproofing must be certification listed and applied in the field as per that listing, using a hydrocarbon fire test curve such as the one used in UL 1709. Fireproof vaults. Fireproof vaults to protect important paper documents are usually built using concrete or masonry blocks as the primary building material. In the event of a fire, the chemically bound water within the concrete or masonry blocks is forced in the vault chamber as steam, which soaks the paper documents to keep them from igniting. This steam also helps keep the temperature inside the vault chamber below the critical 176.7 degrees Celsius threshold, which is the point at which information on paper documents is destroyed. The paper can later be remediated with a freeze-drying process, if the fire is extinguished before internal temperatures exceed 176.7 degrees Celsius. An alternate less expensive and time-consuming construction method is using dry insulating material. This vault construction method is sufficient for paper documents, but the steam generated by concrete and masonry structures will destroy contents that are more sensitive to heat and moisture. For example, information on microfilm is destroyed at 65.5 degrees Celsius and magnetic media lose data above 51.7 degrees Celsius. Fireproof vaults built to meet the more stringent Class 125 requirement are called data-rated vaults. All components of fireproof vaults must meet the fire protection rating of the vault itself, including doors, HVAC penetrations and cable penetrations. See also. References. External links, NFPA standards, fire protection materials and methods.